Hi, my name is Sarah, and this is exploring the function r of x equals x minus 2 times x plus 1 times x minus 3 over x times x minus 4 times x minus 2 with Dory. So based on the equation itself, we can see the many characteristics of r of x. Seeing that there's x minus 2 on the numerator and denominator, we can cancel those out, meaning that there's a removable discontinuity or hole in the graph at x equals 2. After canceling those out, we see that the numerator has two rational roots of x equals negative 1 and x equals 3 after setting it equal to 0 and solving for x and doing the same thing for the denominator. We see it has two rational roots of x equals 0 and x equals 4. The vertical asymptotes are also x equals 0 and x equals 4, since those values would make the function undefined. And the horizontal asymptote is y equals 1, since the degrees are the same on the numerator and denominator, and dividing the leading coefficients together, it would be 1, making the asymptote y equals 1. Now, just like Dory, look at this graph of r of x. The red dotted lines represent the vertical asymptotes, and the green dotted lines represents the horizontal asymptote. And here is a zoomed in version of the graph that shows the removable discontinuity at x equals 2. Just like Dory in this picture, the function is reaching its limits, and we can see these limits on the graph. The limit as x approaches 2, which is the hole in the graph, is at approximately 0.75. The limit as x approaches 0 from the left is negative infinity, as seen on the graph, where it's seen infinitely decreasing, and the limit as x approaches 0 from the right is infinity, as it's seen infinitely increasing here. And the limit as x approaches 4 from the left is negative infinity, as it's infinitely decreasing here, and the limit as x approaches 4 from the right is infinity, as it's infinitely increasing here on the graph. The limit as x approaches positive and negative infinity is 1, considering the horizontal asymptote, and including the rational roots, the limit as x approaches negative 1 is 0, and the limit as x approaches 3 is 0. Overall, there are infinite discontinuities when x approaches 0 and 4, and of course the removable discontinuity at x equals 2. Here I found the first derivative of r of x. Taking out the whole, I then expanded the polynomials and used the quotient rule to find the first derivative of negative 2 times x squared minus 3x plus 6 over x squared minus 4x squared. Then, using the first derivative, I then find the second derivative and apply the quotient rule again, and after expanding and simplifying, the second derivative is 2 times 2x cubed minus 9x squared plus 36x minus 48 over x squared minus 4x cubed. On the graph of r of x, we see its many characteristics. We see the x-intercepts at negative 1, 0 and 3, 0, and though I can see where the function is increasing and decreasing on the graph, I can justify it using the first derivative. I set it equal to 0, and the numerator came up with zeros that weren't real, therefore there's no real critical points. However, also setting the denominator equal to 0 itself, I found the x values 0 and 4, and putting them on a sign chart, it was negative all around, meaning the function is always decreasing, and because of that, there is no extrema. However, keeping in mind the infinite discontinuities and the intervals on which it's decreasing are negative infinity 0, 0 to 2, 2 to 4, and 4 to infinity. Then, to justify the concavity of this function, I used the second derivative test and set it equal to 0, and found that x equals 1.83, 0, and 4. And putting those values on a sign chart, it was negative from negative infinity to 0, and 1.83 to 4, and positive on 0 to 1.83, and 4 to infinity. And where it's negative is where the function is concave down, and positive is where it's concave up. And looking at the graph, my calculations seem pretty accurate. And of course, the vertical asymptotes are at x equals 0 and x equals 4, and the horizontal asymptote at y equals 1. Now, just keep swimming with me. Here's an example problem where I need to verify that r of x satisfies the mean value theorem on the closed interval 5 to 7. Then find all numbers c that satisfy the conclusion of the mean value theorem. First, it is continuous on the closed interval, and based on the derivative I found earlier, it is also differentiable on the interval. Therefore, it satisfies the mean value theorem criteria. Since it satisfies MVT, that means there exists a number c on the interval 5 to 7 where the instantaneous rate of change is equal to the average rate of change of the function. To find these values, we use this general formula and taking the first derivative I found and replacing the x with c, I make it equal to the average rate of change on the interval. After simplifying and everything, I found that c's two values were c equals approximately 5.45 and 6.45, which is indeed in the interval. Now, applying the intermediate value theorem to my function, I chose its rational root x equals -1, and using this theorem, I'm able to prove its existence. Choosing an interval surrounding this root, I replaced the interval on -1.5 to -0.5. Then I found r of x when x equals -1.5 and got 2.25 over 8.25. Then found r of x when x equals -0.5 and got -1.75 over 2.25. Since the value changes from positive to negative, that indicates that the function crosses the x-axis. Therefore, according to the intermediate value theorem, there exists x equals c such that f of c belongs to the interval -1.5 to -0.5. And we know that number is our rational root of -1. We are also able to apply the extreme value theorem on this function. Now, the extreme value theorem states that if f is continuous on a closed interval a to b, then f has both a maximum value and a minimum value on the interval. So, applying this, I limited the interval of this function to -3 to -1, and we know from analyzing the graph before that the function is decreasing from -infinity to 0, meaning that it is decreasing on this closed interval. And so when only looking from -3 to 1, we know that the absolute maximum is at x equals -3 and the absolute minimum would be at x equals -1. Now, let's say we also wanted to find the tangent of a curve of the function. At the point 1.5, 1, we're able to find the equation of the tangent at this point by first using the first derivative we found earlier and substituting x with 1.5, giving us -7.5 over 14.06, which is the slope of the tangent. And since we already know the y value, I'm able to make the tangent's equation using point-slope form first, then moving everything around so that the equation is in slope-intercept form. The tangent equation is y equals -7.5 over 14.06x plus 1.8. We're also able to write the normal lines equation, where you just find the reciprocal of the slope of the tangent, getting the normal line equation of y minus 1 equals 14.06 over 7.5 times x minus 1.5, which is just in point-slope form. And here's the graphs of both lines on the curve together. And yeah, that's pretty much it. Thanks from me and Dory.